Hello and welcome to Lab 5, the final lab, beyond the Slinky Physics. The objective is to try to create a computational model that recreates the actual physics of a falling Slinky. Slinky physics is interesting because as seen by this slow motion video, when the Slinky drops, the bottom part stays motionless until the top piece touches it. This is because the mass or the effect of gravity is not felt by the bottom until the top or the center of mass actually touches the bottom part of the Slinky. And that is the model that I'm trying to recreate using the computer and VPython. The models that are relevant in this VPython module are the momentum principle, which can be seen here as I rewrote it, the spring force, which can be seen here, the drag constant, the gravity force, and I had to break up the number of spring masses into 14 different parts so that it can show the different levels of a Slinky, which will be shown later. The hardest part in doing or calculating how a Slinky drops is first finding out the center of mass. The top blue line right here is the position of the center of mass when it is standing still, which is shown why it's constant. The second or green line is when, as you'll see in my video, it is bouncing from the board that is holding it up, and the last line is as the Slinky is falling. As you can see, the point or center of mass stays completely constant until it comes in contact with the bottom part of the Slinky, and then it drops down consistently. And this is the VPython code that I wrote. Here you can see the number of spring masses that are there, the size or the length of the spring when it is relaxed, the mass of the spring, which I use just the average spring mass, 0.2 kilograms, the spring constant, 15, which I had to figure out through a series of formulas and problems. And here is the formula for the distance of the link. Here is the change in the change in the link. Here is the change in the spring constant, and here is the change in the mass. Here you can see where the distance change formula is and where the spring formula is. This, or the top, is just showing the box as I set it up so that the Slinky would be hanging from a wall at first, and then after it drops from the wall you can see the process of a Slinky falling. Down here you can see that the code looks a little bit complex because I set it up to run an index so that when I ran the code it would actually produce a series of values that would create the graph that was shown earlier and that will be examined later. Here is some more of the code, and here is the rest of it. If you would like to examine the code more, you can pause the video and go back to the previous frames and see exactly what it looks like. When I run the program, you can see what happens. As I said, the Slinky is at first hanging from a mass and bouncing up and down, and the moment it stops bouncing, then it will drop from the mass and you will see the motion of a Slinky as was shown in the video earlier. As you can see, the top part drops and the bottom part stays completely still until it hits the bottom part, and all fall together. Here's the values that I ran it to print, and once again I'll run it again so that you can see. I'm running it again so you can see exactly what happens when the Slinky is dropped in the VPython model, or at least I'm trying to run it. One second. And this is intricate because it shows that the bottom part didn't move because it did not receive the information that from the top part that it should be moving. At that moment, the bottom part has no specific center of mass, so gravity could not pull it down and would not have the effects of gravity and fall down to the earth. Alright, so once again I'm going to go over all the relevant models that were used. Here you can see that the momentum principle was used to predict the position of the ball, and that I had it predict the center of mass so that the Slinky would not fall before the time it was supposed to. And if we go back to the PowerPoint, you can see that the drag constant, the spring mass and the spring force and momentum principle are used, as the Slinky is just a gigantic spring. And once again, the center of mass graph, the blue line showing the center of mass when it was standing still, the green line showing the center of mass when it was hanging from the box at the top, and the red line showing the center of mass as it was falling. Thank you for your time. Hope you